Hello and welcome back. We'll start this video, again continuing section 3.5, by using a graph that we're already familiar with, that we saw in a previous video, graph of 1 over x, and then we'll transform that to graph 1 over x plus 2 minus 1. So we know that the graph of 1 over x will look something like this. It has a vertical asymptote at 0, as a horizontal asymptote also at 0, and the way that this one way to identify this is at x is equal to 1, the height of the function is 1, since 1 over 1 is 1, and at x is equal to negative 1, the height will also be at negative 1, since 1 divided by negative 1 is negative 1. So this is our original function. This is 1 over x. So here, what we can look at is we have added 2 directly to the x. So we can graph 1 over x plus 2. And what we know is that any time a graph, when you add a number directly to the x inside of the function, we have shifted the function to the left 2. So 1, 2, 3. Let's say there. So now, instead of having this point be at negative 1, we'll be at negative 3, negative 1. And this point here, that 1, 1, we've shifted it to the left 2. And our vertical asymptote, which is right here in the middle, we've shifted that left 2. So now our function looks something like this. Okay, so we just shifted that to the left 2. And then the last piece of this will be to subtract 1 from the whole thing. If I just put parentheses around this, this will be a little bit clearer. So if I subtract 1 from the function, it means that we're shifting everything down 1. So again, if we have our graph up, 1, 2, 3, and now I'll have to go down 1. The vertical asymptote, which was at negative 2, is still at negative 2. We've only shifted everything down. So this point here, which is at negative 3, 1, is going to be at negative 3, 2. This point here, which was at negative 1, 1, is now going to be at negative 1, 0. And the horizontal asymptote now, which had been at 0 every time, is now shifted down 1. So our function now looks like this. So we can see that we've transformed our function by shifting it to the left 2, and then shifting it down 1. So here is our function of g of x, just using things that we already saw before. So a general strategy for graphing a rational function, it's got a few steps, but each one sort of makes sense, and it's things that we have already done before. So let's assume that we have a rational function, a polynomial divided by a polynomial, and we're going to make one big assumption that the top and the bottom don't have any common factors. If they do have common factors, we'll just have to reduce the fraction until they don't. So the first step is to see if there's any symmetry. See if there's a y-axis symmetry or origin symmetry. If there's symmetry about the y-axis, this means that what we have is an even function. And if there's symmetry about the origin, this means that what we have is an odd function. Again, to check this, you plug negative x into the function and see what you get. If you get the original function back, it's an even function. If you get negative of the original function, we have symmetry about the origin. So that's the first step, see if there's any symmetry. The next two are, again, things that we've been doing already, finding Y-intercepts and finding X-intercepts. The Y-intercept is when the function will cross the Y-axis, which we could just plug in x is equal to 0. Or when we're finding the X-intercepts, we want to know when is the function equal to 0. Now, our function is a fraction. So when is a fraction equal to 0? When the top of the fraction is equal to 0. So I don't have to solve this whole thing is equal to 0. All I need to do is look at the top of the fraction, and that will tell me what the X-intercepts are. Then I can find the vertical asymptotes and the horizontal asymptotes. Again, the vertical asymptotes, all I need to do is see where I'm dividing by 0. Since there are no common factors, that's it. So all I have to do is see where the bottom of the fraction is equal to 0. The horizontal asymptotes, this was looking at the leading term in both the top and the bottom and seeing which has the higher degree. So this is the method that we saw in the previous video. And then what we want to do to make sure that we're graphing everything right is to plot at least one point between all of the important data. So we could plot 1 point in between all of the X-intercepts and vertical asymptotes. So this will give us enough information to be able to plot the graph well. So let's go through an example. Let's graph f of x is equal to 3x minus 3 divided by x minus 2. And what we'll notice is that this is reduced. If I try to factor the top, I could factor a 3 out. And now this is completely reduced. And then on the bottom, I can't reduce that anymore. That's just going to be x minus 2. And there are no common factors on top and the bottom. The top has the factors 3 and x minus 1. The bottom has factors x minus 2. So it only has the one factor. Okay, we're good to go. Number 1 was looking at symmetry. So what I want to do is I want to plug in negative x into my function and see what I get. If I plug negative x into my function, I'll have 3 times negative x minus 3 all over minus x minus 2. I can simplify this a little bit, and I'll have negative 3x minus 3 divided by negative x minus 2. So right away, we see that this is not equal to the original function. This is just not the same thing. Negative 3x minus 3, I have the 3x minus 3 on top. Those aren't the same. But this also isn't the same as negative f of x. If I just plop a negative sign in front of this, I don't get this function. So it's neither odd nor even. This function won't have symmetry about the y-axis, neither will it have symmetry about the origin. The second thing that they ask us to look for is the y-intercept. So let's plug in 0 into our function. So this will be 3 times 0 minus 3 over 0 minus 2. 3 times 0 is 0, minus 3 is just negative 3. 0 minus 2 is just negative 2. So 2/3, this is the y-intercept. Cool. The x-intercepts, again, I want to solve for when this fraction is equal to 0, but a fraction is equal to 0 only when the top of the fraction is equal to 0. So I just want to set this equal to 0, and if I add 3 to both sides, I get 3x is equal to 3. If I divide 3 from both sides, I get x is equal to 1. So this is, so 1 is the only x-intercept. So our function isn't going to be symmetric in the ways that we've seen before. It has a y-intercept. It has one x-intercept. Next, we want to look for vertical and horizontal asymptotes. Well, vertical asymptotes are going to be where we divide by 0. So when is the bottom equal to 0? So when is this equal to 0? Well, if I add 2 to both sides, see that x is equal to 2. This is our vertical asymptote. And then furthermore, with the horizontal asymptote, we look at the degree of the top and bottom of the fraction. So on top, our polynomial has degree 1 because it has an x to the first power, and that's the largest power. On the bottom, we have x to the first power, and that is our largest power. So the degree on top is equal to the degree, which is 1, is equal to the degree on bottom, which is also 1. So what we do is we say that this does have a horizontal asymptote, and the horizontal asymptote is going to be the leading coefficient divided by the leading coefficient. So there is a horizontal asymptote, and it's going to be y is equal to 3 divided by 1. 3 being the leading coefficient of the top of the fraction, 1 being the leading coefficient of the bottom of the fraction. And then we want to plot a point between the X-intercepts and vertical asymptotes. So let's start plotting this as best as we can. So we know that we have a Y-intercept at 3/2. So if I go 1, 2, 3, 3/2 is 1.5. So there's my Y-intercept. If I go 1, 2, 3, we have an X-intercept at 1. And we have a vertical asymptote at x is equal to 2. And then we have a horizontal asymptote at y is equal to 3/1, which is the same thing as y is equal to 3. So here is our horizontal asymptote. So we can begin to see that over here, our function is going to be going down, and we're going to be coming up and coming across. The question is, what happens on this side? Are we going up? So does our function look something like this? Or does it look something like this? We don't know. So what we'll just have to do is use number 6 and make sure that we plot some points in between these guys. So here we want to know what happens on this side of our function. So for instance, let's see what happens at 3. F of 3 is going to be 3 times 3 minus 3 over 3 minus 2. 3 times 3 is 9, minus 3 is 6, 3 minus 2 is 1. So the function value is going to be 6, which is going to be way up here. So our function is going to do something like this. So there you have it. We just follow the steps, and we can see that this is what our function will look like. I'll go through another example in the next video.